coming from TTI Chicago. He actually was showing up in Chicago right when I was leaving. I met him on the way out, but we've gotten to know each other since. And today is going to be talking about some interesting work in discriminative training, as well as some interesting work in voice onset time protection.
Hi, thanks for having me. Hope you forgive me for the title. So what I try to explain, what I try to present is several works. At least I'll present two of them, which are so my work is focused on machine learning and on kind of signal processing for speech recognition. I'll try to address both of them. I try to present at least 2 or 3 works, and at the end I'll try to present the work I'm doing now. Please stop me if you have any questions. So this is how I see speech recognition nowadays. So it's like an old lady with hearing problems. So we have the we have the acoustic features, which are kind of problematic. It's usually, as you know, it's usually sampled at 10 milliseconds and span a window of 20 or 25 milliseconds of the spectrum. There is acoustic modeling, which is a kind of machine learning model that try to address the sequential behavior of the features. So if the features try to bear the information from the signal to I don't know, a lower representation, the acoustic modeling try to take those the signal and extract phoneme or subword units. Then we have pronunciation model, which try to take those subword units and have them as a word. Pronunciation modeling should address problems in reduction of pronunciation, of course. And then we have the language modeling, which try to address the combination of words into hopefully grammatical sentence. And it should work in a different environment. It should be adaptable to anything, and usually it's trained on a speech corpora. But anyway, what I will do is like present work on 1, 2, 3, like from acoustic modeling to acoustic feature, acoustic modeling, and pronunciation models. And I'll present, along the way, I present the problem in each of them. So this is a graph that I'm sure all of you have seen before. So this is the range of human error in transcription. Last week I was visiting John Allen, a friend of Hinek, and he also claimed that this is not correct. Actually, the human error is like around 1%, even less. So this is the database we use on speech. This is the NIST evaluation over the year. So you see the year along this line, and you see the word error rate according to this line. And each color represents a different data set. This is really easy, red speech, and this is air travel. This is maybe our resource management, and this is switchboard. And you see CTS, which is like, I think Siri is a spin-off of that data, I think. And what you see is like the performance along the years. So you see that the performance are going down somehow. But if you look carefully, the trend is not like the human error, which doesn't go down along the years. So the question is, where are we heading? So in this talk, I'll first present a phoneme alignment algorithm with the direct cost minimization. So it's going to be a combination of the machine learning work and the work I've done on phoneme alignment. And then I'm going to present the phoneme recognition also with direct loss minimization. So this is linear models like structural prediction, SVMs, CRF. And this is something else. This is a more general case for the HMMs. Then I present a different work of which I'm really excited. This is what I'm doing now. It's about VOT measurement. VOT is the time between the burst of the stop consonants and the vowel that after that. And this is something that humans and animals are really try to. It's something really perceptive, something really that has to be really accurate in order to use that. We use that in linguistics, in phonetic study. We use that in speech analysis for different kind of pathologies. And this is really exciting work because it's working. It's something that we use now in phonetic studies, and it gives we can answer questions that we couldn't done before, because now what happened in the phonetic labs, this is the most important value that they measure, and this measurement, it takes, I think, thousands of hours of students each year, and now it can be done in a few seconds. And I will finish with the current and the future work. So let me start with direct loss minimization. What I'm going to do is like present that as along the application of the forced aligner. So we have the speech signal, we have the phonetic, we have the word transcription, the orthographic transcription of it, he's bought it, and we have the phonetic transcription. And what we want to do is like to align we want to align each phoneme to the location in the speech signal. Okay, this is the task. We are given the speech signal, we are given the phoneme or the orthographic transcription, and we want to find these locations. Like H is going to be in the first frame, time, I don't know, 0. This is going to be in time 7 milliseconds. This is going to be time to 200 milliseconds and 7. I don't know what. So we want to find this sequence of locations. This is a really nice problem for the direct loss minimization, because it's a simple problem, but it has a different, very nice cost and loss functions. So we take the speech signal and we convert it into features, acoustic features, the standard features of MFCC, which are taken every 10 milliseconds and span a window of 20 milliseconds. So this is the acoustics. We take the words and convert them into phonemes by look up at a dictionary, a lexicon. So the notation here is like I denote the features with X bar. Bar means a sequence, and it's boldface because it's a vector. It's a sequence of vectors. The phoneme is P bar, which is a sequence of phoneme. And we want to find the sequence, the alignment sequence Y bar, which is a sequence of times, which is given in terms of the frame number. So this is like frame 0, this is frame, I don't know, 3, this is frame 17, and so on and so forth. So we would like to predict Y bar. Okay?
Why would you prefer the boundaries rather than centers, for instance?
Why do I prefer what?
Boundaries between the phonemes rather than the centers of the phonemes. Would it be
The center?
Center. Where the phoneme sounds. Do you think that?
Yeah.
Do you think that the boundaries are important?
I don't know. I saw like this is the way traditionally it was done. I don't prefer. Actually, the center, the core of the phoneme is much more accurate. But this is the definition of the problem. It's just an example problem how to use the cost minimization. So we define it as the beginning of each word.
Not necessarily, because the center doesn't define the boundary. The boundary may define the center in some ways, right?
No, but if I have 10 phones, I know the beginning and end, and I give you the 10 center point.
That
I
is,
also give you the 9
that is certainly true, but what is easier to get, boundaries or centers?
But that's a different story.
Yeah.
That's what I
Problem is equivalent.
yeah.
But
I don't
none
think so.
None of it's not symmetric.
I don't
mean,
think so.
The center where the most information lies is not necessarily the mean of the boundaries.
Yeah.
Then you have to tell me what you mean by center. But anyway, yes.
Yeah. The core of this IY.
You are right there.
It's what the timid guys wrote down.
Right.
The boundaries is what the timid guys wrote.
Victor says, right?
But I think that it's not the same problem. The core is like somewhere here. The boundary, like specifically here, or if it was nasal, can be like shifted. But there is, if you look at the signal, there is a huge gradient there. So this is the problem. We have the acoustics, we have the phoneme, and would like to predict the alignment sequence, the sequence of start time. So what's interesting in this task is like how do we assess the value of how good is that what we have? So we have the predicted sequence, Y bar prime, and we have the presumably human labeled sequence, the Y bar, and we would like to compare them. So one way to compare them, this is the standard way people do compare them, is the number of times the difference is greater than tau. So if this difference is less than tau, we don't count it as error. But if it's more than tau, let's say here we count it, this is 1 error, this is 0, this is 1. So maybe, I don't know, it's like 3 divided by 5, 6. So maybe it's half. So this is one way, just counting how many times it's greater than tau. Tau usually it's, I think, 5, 10, 20, and 30 milliseconds. There is another way, which is, it's called the tau insensitive measurement, and then we count. So if the difference is less than tau, it's 0. If it's more than tau, it's not just 0 and 1, we just have some kind of slope, and if it's really, if this is 17 and this is 3, the difference makes a difference, and it's going to be 17 minus 3, and it's going to be 14, which is not like just 1. So this is a different cost function. So we have those cost function. If you want to minimize those cost function, or if you want a model, you want to minimize those cost function, it's not that easy. This is a combinatorial value which has like a lot of, it's not differentiable, it has a lot of minimas. So the ultimate goal is to find an alignment function which will minimize that in expectation. In expectation, it means that on unseen data, on data which we don't see, but coming from the same source of the training set. So the expectation is taking over a sample of X, the acoustics, and P, the phonemes, and Y, the alignment, the human label alignment. So we assume this linear model for time being. I'll speak later on how do we extend this model, but for time being, let's assume that we have a linear model. This linear model is a combination of two parts. So we have W, which is a weight vector, and Phi, which is what we call feature maps. And each of them is of length n. And what I'm going to explain now is what are the feature maps I'm using, and then I'm going to explain how to train W so as to minimize the expected loss. So the feature maps have to be high if Y bar makes sense given X and P. We are trying to enumerate for all possible Y bar, all possible alignment, and if Y bar makes sense given X and P, it needs to be high, otherwise it needs to be low. And this is just a general guideline. It doesn't need to solve the problem, those fees. It just needs to be high if it makes sense and low otherwise. Then we multiply each of those phi by W, and it's like a weighted phi, and we would like to have our prediction to maximize those two. So first I'm going to speak about those phi function, and I'm going to do it really quick. So one example which related to the boundaries and not to the core is like the distance. So we have the boundary, we have the frames. So assume you have two green frames and two blue frames. And if the boundary makes sense, if Y makes sense, we want phi to be high. So if this boundary makes sense and we look at the distance between this and this, between those two frames, it's going to be high. If this boundary doesn't make sense, this is going to be low. You can see that in the spectrogram, this is going to be high. There is a gradient there. And this is going to be low. And we have different features. We have another feature which take into account the posteriors along the sequence. So we assume that we know the phoneme sequence. We just don't know the boundaries. So if the boundary makes sense, this the sum over the posteriors should be higher. Okay, if this boundary, for example, makes sense, this sum should be higher than if this doesn't make sense. And then we count, for example, the posteriors for B, while the correct phoneme here was AO. This is more related to the core part of the phoneme. And then we have some model for the duration of the phonemes. You can see that the whole thing is like a segmental model or segment-based model. So we have the duration of the model. If the duration of AO makes sense, it's supposed to be longer than the plosives, then it would have a higher score. Otherwise, it will have a lower score. And then we have a model of the speaking rate. So we just look at the speaking rate we just look at the production of the phoneme a long time. It has to be steady. I mean, you cannot speak very fast and very slow at the same time. And so those are the phis. They're supposed to make sense again if X and P are if Y bar is relevant to X and P, and otherwise they don't. Now we need to train W. So we want to train W so as to maximize the loss. I wanted to note here that this model W dot phi is exactly the match filter if you assume Gaussian noise. I spoke a lot about match filter today. So this is exactly the match filter if phi were linear, and if you assume Gaussian noise, this is exactly the match filter with a map estimation. So how do we find W? So again, recall that this is the goal, and we want to minimize that. So what we do is like we want to find W so as to minimize the loss. So usually what we would do if we were in taking a first course in phi, we will take the gradient of the expected loss. Taking the gradient is not so easy. So we would take the gradient and compare it to 0. This would find the minimum of this function. This is hard because sometimes you cannot take the gradient directly. What we assume here, nevertheless, is that the gradient of the expected loss exists. Okay, we don't assume that the gradient of the loss exists. We assume that the gradient of the expected loss exists. It's called the proper positioning of the loss. And then taking and comparing it to 0, it's also very hard. If we could find the gradient, we can do something like that, which is a gradient descent type of algorithm, stochastic gradient descent algorithm, that go over the examples, and for each examples update according to the gradient of this loss function. So how do we do that?
Before you go too far, can you go back to the basic feature definition or just yeah. So in this setting, you obviously assume that phi is a fixed dimensional vector.
Right, right.
Even though the length of x and y bar varies from example to example. And some of the features you described, they looked like there would be one of them for every possible boundary. So if y bar had, let's say, k boundaries in it, there would be k places where you would look at whether the two sides are sufficiently different. There would be k plus 1 places where you would look at
Right.
the durations are sensible. You want to say a bit more about how you go from the variable number of things to a fixed dimensional phi?
Yeah, okay, so the idea here, I have a misnotation because the p is missing here.
Yeah, that's okay.
But this is the general case. So the whole idea of phi is to make the variable length sequence into one. So maybe I didn't explain that. So usually we sum over the phi. So we do something else, or we take the max, or we take the mean. But we have for each feature, we have one real value. So if you consider, for example, the boundaries, we know, because we know the phonemes, we know we have k phonemes, so we just sum them. So we know we need to sum k boundaries, and we have one real number for all the distances. We can sum all the duration, the presumed duration. We can sum all the speaking rates. We have one number. For each of those, we have one number. And then you have a full signal, but you end up with one number. So overall, we have n of those.
And is it important to normalize by the number of this number k, different examples with different numbers? Do you sort of normalize?
No, not at all. No. It will be more extreme in the third example that I will show. So we came up with this theorem, which looked a little bit odd at the beginning, but it's really really nice and important, and has a lot of intuition into that. So let me present that first. So what we have here is we have two predictions. One is the prediction with the model W dot phi. Again, p is missing, p is given, so you can assume that it's part of the x. So we have W dot phi. This is the standard prediction we are using in this model. And then we have another prediction, W dot phi plus epsilon L. L is the same loss function, the same cost function that we used that I presented, this particular loss function. And this can be computed easily with a dynamic programming because this is separable. It's separable in the number of phonemes. We multiply it by epsilon. So now the theorem says that the gradient of the expected loss is going to be this thing. So this is phi. When we plug in instead of y, instead of the boundaries, we plug in this prediction. And here, instead of the correct boundaries, we plug in this prediction. So we have two predictions plugged in here. Okay. So if you look at if you look at that carefully, if you plug in, if epsilon equals 0 in this case, those are the same, right? And this is going to be 0. But if it's not 0, if epsilon is not 0, just a little bit above 0, what we get here is exactly the gradient. And I'll try to explain you why is that. So this is the definition of the gradient. If you remember the basic definition of the derivative is over there in yellow. And what we did here, this is exactly the definition of the gradient. Okay? And this is one side of the theorem. The other side is this thing. This is the theorem itself. This is the gradient. And what we did is we showed that the right-hand side of this part and the right-hand side of that part are the same. You can do that by explicitly write this expectation is integral over the decision boundary between this and this. I put here W, but it's the same as without W, okay? Just to make it clearer. So this is an integral over the decision boundary, and this is also the integral over the decision boundary. And when epsilon goes to 0, those are equal. It's not approximation. They are really equal, both of them. I have a slide showing that, which I skip here. So this is the decision boundary, the blue surface, okay? So one side of the theorem, I call this delta L, L minus L. So this is the surface, and we're going to do integral over this surface multiplied by some terms. So this is delta W, and delta phi, which is phi minus phi there. So we're going to, this is just to give you the intuition about the proof. So it's the integral over delta L times this. The other theorem in blue, it's the integral over delta phi multiplied by delta L. And the whole thing equals the same, equal this term. So this is how the proofs go. The rest is just mathematics. And this is the algorithm. I guess you understand from what I said before. So you just predict with the previous W. You predict with the previous W, but with a loss adjusted. And then you update it like that. Okay, and you have to tune epsilon so as to be minimum, but not minimal, that those are the same. So how we tune epsilon is like we compute that and we say, okay, let's have like 80% or 50% of the training set having difference between the predicted one and the loss adjusted one and the predicted one. So here are the results for this exactly phoneme error rate. So in the first line you see this is standard HMM system with additional features, Brugnara et al. 93. This is why we use the same setup. Keshet et al. Was a work that was done in my PhD. This is a structural SVM. This is SVM. And Hossam 2009, it's the best system so far. What the number here are is exactly the loss that I wrote there. So t less than 10% means that we count error. This is tau, so it's like we count error as everything that is less than 10%. So 86, 79, for example, means that 79. So this is not an error. This is accuracy. So it means like 79.7 of time, the correct boundaries were within 10 milliseconds. Okay. This is the percentage within the correct boundaries. So those two are the system I presented here. When one of them is trained on the tau alignment, and the other was the tau insensitive. And you see it's huge difference. Like it's like see for the first column, 86 compared to 79. This is huge difference. This is almost as the inter-cyber agreement on this data set. So this is just an example. I didn't do anything. Those two results are they have the same feature, the same setup as the second one. This is exactly the same.
Maybe you said it, but this is ultimate, is it? Or
this is ultimate, yeah.
is it also similar on some other databases, or?
I don't have the results here. I'm using it later on in the talk on switchboard. Yeah, this is just Timid in this setup.
I would assume not, because on switchboard, for example, the
this is everything Timit. These numbers are also according to Timit. It's not that published.
Yeah. No, what I'm saying is that Nick was wondering whether this would be similar on switchboard, and I'm saying no, because even humans can't agree on the
Yeah.
So I don't know if the machine will do as good as this. So because I remember, I don't know if the number is published, but when they were transcribing switchboard phonetically, they had a lot of problems pegging down phone boundaries.
But that's where I'm aiming. I mean,
Right,
sort of, you know, I honestly, I mean, actually you answered, so somehow got called on my question, which is like, so we're comparing to labeling done by MIT, right?
Yes.
Is this what we really want to compare to or not?
No, I would say it's labeling done on carefully articulated speech versus...
But by humans.
In both cases, by humans.
This is, you can, like this task, I don't know, you can argue if it makes sense or not, but this is, I just wanted to present the algorithm on that
No,
one.
I don't question
This is the result. Yeah, he claimed, Hanson, it's the best result for the team so far. So apparently those guys, so I'm coming from electrical engineering, from speech recognition, a little bit from machine learning. Those guys, they are Percy Young, Alexander Bouchard, Cote, and Dan Klein, and then there is Ben Taskar there, who is David Chiang, Kevin Knight, Wei Wang. All of those guys, they are from machine translation. So first when I put those pictures, I was shocked. Everybody's happy. We are in speech recognition, we are really sad. We are not that happy. Except from Ben Taskar, he's from machine learning, he's a little bit... So anyway, those guys, they know something we don't know. So in those work, which are really important work, both of them use direct loss minimization. This is the work of this is the work of Ben Taskar. So here the blue is in plus and we use minus because blue is like, it's not loss, it's utility. And there is the work of Percy Young, which also, it's hidden here. This is what they call update toward the option with the highlight blue score. Let me now go to a different model, which is more extended model for the direct loss minimization, direct cost minimization. So we have an HMM model, and I put here P of X and S. S are the states, and theta is the model parameters, okay? So this is the HMM. We have a starting state. We have the transition between the states, and we have the emission probability. This is the subtle HMM. And I think during this part, I'm presenting one state per phoneme or per word, but you can use many states just for the clarify. So again, bar means a sequence, or S bar means a sequence of states. And the question is, how do we minimize the loss or a cost function? So the main works on that, the MMI, the MC, and the MP, MWE, are amazing because before we just look at that like minimizing a loss function only now, and those works are, I think, from the first one is 97 or something. This is amazing that how come that the speech community is always before the other communities. Most notably is the work of Dan, MP, MWE, because this work is actually minimizing the thing we want to minimize. This is the expectation, okay, of the probability of the loss divided by the probability. This is really related, this is hardly related to the direct loss minimization. So if you look at the denominator here, and you take a log, this is exactly the same thing. And this is, so we have two predictions in direct loss minimization. One of the prediction is this one, and the other is that one. And what I'm trying to do those days is like to prove that this is also consistent. I show half the way that this is consistent to the base optimal solution. It's not done yet, but this is like the right thing to do if you want. So in that sense, this is the right thing to do. This is the way to minimize the loss. Another work that was done was trying to find a large margin online training, and then those guys, Chiang and Fei Xia and Larry Sol, they try to have a prediction which is loss adjusted with raw. Okay, this is the loss. This is word error rate or frame error rate. This is the standard likelihood, and the rho is a parameter which they can call the margin. And the update rule is as follows. They put here the correct sequence. They put here the rho adjusted sequence, this sequence. And this is the update rule for a margin-based HMM. I put here derivative according to theta, but this is something analytic. I cannot, it's like too long to put that here. But if you assume GMM and stuff like that, this is there is an analytical solution to the gradient of the log of the P. Okay, so this is the theorem for that case. So again, we have a prediction. We have a prediction which is loss adjusted. And then we take the derivative of those terms. The derivative can be computed analytically. And we have one term which is the epsilon loss adjusted, and one term which is just the prediction. Both of them they can be computed with the Viterbi algorithm. Okay, so this is the theorem. This is also holds. And as you can see, the target sequence in all of those algorithms come into account only by the loss function. Okay, so you can think about it as we try to steer our update rule toward the loss. So this is the algorithm, again, predicting and plugging it in. What I wanted to tell you is like, okay, if this was the correct sequence, you get the large margin update. And if this was the correct sequence and you plug here S prime, not S prime epsilon, just S prime, you get the perceptron update. So this update is something in between the perceptron update and the large margin update. Again, I try to look at it as the denominator of MPE or MWE and the denominator. So those are the results. I took a Chang system, Chang and Larry Sol system as is, just plug in the update rule, and you see it's like lower for every number. This is one is with phoneme error rate, the previous is with frame error rate. Do you have any question before I continue to the second part?
So it seems like on this last couple of slides you were adding the loss in, whereas it seems like the thing you were updating towards was the thing you found by taking the argmax of the model score minus the...
Yeah, you can play with that. You know, the gradient you can define as plus epsilon minus epsilon. So I could put like a minus epsilon L over there and plus here. You can put minus and plus. You can play with that as long as you keep the correct direction.
And there's no, I mean, whatever. Like, have you seen any? Does it make any difference or any else?
Yeah, minus work much better. If you put minus epsilon in the previous scenario, it's much better because it's like. I think it's like it's more similar to the structural prediction. You're going into the direction of the loss. This is like to go in the negative direction of the negative loss. I don't know if there are.
So why did you do it plus?
Because it was easier to implement. I took her code, just plugging it there. They have the code for perceptron. I don't even remember. It was so easy, like to change the code because of laziness.
So is this like a form of, it's a bit like MPE, but there's kind of powered boundaries somehow. Is that right? I get the impression that on the left and the right there may be two different transcripts that you got kind of with epsilon, without epsilon.
Right. There are two different transcripts. One is like more adjusted to the loss, to the frame error, and one is less. And you try to update.
Okay, so if the one on the right-hand side was, let's say, the transcribed, the human transcribed one, then that would be MMI, I guess. Oh, sorry, if you had taken one of them to be the correct
If this is the correct one, you want to make it in the plus the correct one and the minus the bad one. This is the good guy. This is the bad one.
It's going to be worse transcript than the
Yeah.
other one.
If you put here y, this is like a large margin. And I think large margin is the MMI. I think it's the same. It's close to the...
Oh, Okay, so the Y is the...
No, MMI is like perceptron. Sorry, I think MMI is like perceptron. It's like putting the right here and here. It's like without the epsilon, like epsilon equals 0.
Okay.
But the connection is not there.
Okay,
Like,
so which is the worst transcript? The worst transcript is the one with epsilon or without? Okay.
yeah, but you cannot think about it like that, because when you don't have the correct one, what matters is like the difference between them. I could put minus epsilon here and without epsilon here, and
so if epsilon is small, it doesn't matter, I guess, whether it's minus or plus epsilon, because it's small.
yeah, only if you take the right direction. Yeah.
It still matters. I mean, because yeah, you want to make sure you get the
You can put minus epsilon here and plus epsilon here, and that might be faster. I spoke with the...
And if I remember, the work by Chang et al. Does both. You know,
They do both.
Given an answer, they say, let's try to find a lot of things which, a lot of slightly worse things and a lot of slightly better things in terms of loss, but which are close to, which you can almost achieve with the current weight vector, and then update more of the better things away from the worse things. So Yossi's, on this slide, is updating away from a slightly worse thing, and on an earlier slide, as Adam pointed out, he updated toward a slightly better.
This is the fastest option. It's like
Which
like with minus epsilon and plus epsilon. It's like somehow fastest than everything else.
Converges faster.
Yeah, so I spoke with McDermott about, I remember, I spoke with McDermott if we can come up with a rule like the MPE, which has like the numerator and the denominator have both terms. I don't know, I mean, we didn't come into conclusion with that. So those are the numbers. So let me speak about a different work, which I'm really excited about. This is what I'm doing now, most of the time. So VOT is the duration between the burst onset and the starting of the voice. This is really important in many, many aspects of speech recognition. So we know we have, sorry? So we know we have a, how do you call it, perceptual categorical perception. So I try to somehow simulate that by this plug. So if the VOT is less than 25 milliseconds, we think it's a B. If it's more than 25 milliseconds, we think it's P. And actually, the VOT is something that is moving smoothly, but perceptual is different. This is in the standard production of B and P. We will see later on that in extreme production, this is not true. So we know that infants at the age of 1 to 4 months can detect that. We know that even chinchillas can detect that. It's a very known science journal. So they try. So what they do, they swipe the VOT along the way from I think it's T and D, and they detect that. It's a cue for the place of the location and the place of articulation. It's really important in disordered speech, and so it's a main tool in analyzing phonetical studies like speech production, speech errors. The last interspeech, there was a paper about depression and VOT. So with the collaboration with Zach Shafran for OHSU, OGI, what we try to do is like people with Parkinson's disease have to go to be examined every month, I think, to say how shaky they are. It's called the MUPDRS, I think Motional Universal DMP, Parkinson's Disease Score, MPDRS. So this is a number between 1 or 0 and 109, and we try to predict that. So those people are now calling to a call center, and they say pataka, 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 and we analyze their voice. And according to that, we estimate the UPDRS. This is really nice work. So we try to. So there are several works on that, but somehow none of them are really applicable to a huge data set. And some of them, even most of them, use MFCC. So I have to tell you that the VOT can be as short as a few milliseconds, and the MFCC span a window of 20 or 25 milliseconds, and you cannot just shrink the MFCC. So we need to come up with a different signal processing here. But anyway, whenever we even look at the App Store and the Android store, there is no app for that. You cannot take an algorithm and use it like for a huge data set. So let me define the problem again. So there is a time of the burst. There is the time of the voicing, TV and TB. This is what we call a positive VOT. It's like when you say bye. There might be a negative VOT when the voicing time is before the burst time. So there are languages that have that, like Spanish and Portuguese and many Indian languages. In Hebrew, we don't have negative VOT, but what happened is like there was a show for like teenage girls and something, so they wanted to say, we say bye in Hebrew, like in English. So they wanted to say bye and go away. So the combination was bye. So we put the pre-voicing, so now we have pre-voicing in Hebrew. There is the bye is like pre-voice for bye. Anyway, so in this work, we define a loss function, which is uniquely determine the VOT. It's similar to the loss function of the forced liner. And again, we would like to minimize the loss function. We have the same model. This is the match filter model, a linear model. We have a training set of examples. The training set of examples includes some acoustics features, which are not the MFCCs, and the time of the burst and the time of the voicing. And then we have we define the acoustic from scratch. What we did is like we sample the signal at 1 millisecond and span a window of, it's a mistake, it's a span a window of 1 or 5 milliseconds. So we have 7 features like that, 7 acoustic features. One of them is low energy, high energy, winner entropy, total energy, autocorrelation function, zero crossing, voicing, the pitch, the voice, like the voicing of the pitch, and all those functions are sampled at 1 millisecond. And you see that there is somehow correlation. This is the time of the burst. This is the time of the voicing. There is some correlation between what happens with the features and the actual burst. And
What's the speech signal that you remember?
it's before. I don't remember what was the. I can look it up.
Because I see 2 of them and I'm
You see what?
I see one. In the beginning, I know you're showing me the voice onset gap from 0 up to 120.
Right.
Right. But then there's another thing which looks a whole lot like it. What is that gap over there? Or I guess it's just.
I don't remember what was said here.
3 and 400.
But it's not similar because this algorithm like works really well on that.
No, I'm saying I'm just looking at the features, and for example, on the first graph, red is above blue, on the second, blue is above red, and on the third one, it's blue, red, green, and that repeats again, and the voice.
This is the same signal. I just plot like 2 features in each figure, but instead of plotting all of them together. And you see that some of the features are high at the burst at the voicing time, some of them are high at the burst time. And we need somehow to combine them together. I forgot to say that we are not synchronized to the beginning, of course. We are not saying that we are taking after 20 milliseconds. It's not synchronized. You have a signal. You have a word. You can span a big window. You can span a short window. The only thing is that you will have at least 1 VOT there. And then the algorithm will spot the first VOT. So what I want to describe now is how do you choose phi. So those phi functions are just, so what we did is like we go to those phoneticians and they label their VOT for all their PhD, and they say, okay, first I look at the high energy and I see that there is a raise there, and then I put TB, and then I look at the low energy and I see there is a raise there, and then I put TV. And they describe the process for us, and this is the way we build the feature. We have 59 features like that. So here, for example, you see 1 feature of those. Again, it's like it's supposed to take any sequence length and convert it into 1 real number, each feature. Okay, so one of the features is the mean from the beginning of the signal to TB, and then the mean of the signal from TB to TV. And you see this mean is going to be high if those are in the correct location, and if it's not in the correct location, you see it's going to be lower. The difference between them is lower. Okay. So we have 59 features like that. The maximum of the feature, the sum of them, the mean of them, the mean minus the mean, which is denoted here by delta, and all of those features designed by hand to this problem. And it was, it was according to the work with the phonetician. And we train W with a passive aggressive. This is standard structure prediction. Large marginal algorithm. We just predict and plug it in here. This is the true TB and TV for the example M. And this is the predicted TB and TV. And we can show, this is something old, we can show that this is also converges to minimizing the loss under some condition. And it's compatible with the best predictor in this class. So here are the results. So we compare our approach to other people, specifically for Staudt and Van Ham. So what you see here is like, again, how many times the VOT was within 10 milliseconds, for example. So in our algorithm, which is blue, you see it's a little bit below, sorry, Staudt and Van Ham, it's a little bit below 80%, and our algorithm is a little bit above 80%, so higher is better. And we compare it to Lin and Wang.
Can you go back to that point for a second? Yeah. So I guess this is simply the cumulative, right? And
right.
The thing is, like, I guess the more difficult cases are the short ones, right? Because
yes.
So can you say something about how many of your tokens the reference VOT was less than 5? Is that?
No. Well, I can show you something else. So this is comparison to those guys, Lin and Wang. This is actually can run only on 5% of TMIT. We are not interested in TMIT in this setup, and TMIT is really small. But so what we did is like we took switchboard, and this was hand labeled in University of Chicago with a phonetician there. So what we did is we compare our model with the manual transcription, and we compare several. So there were 5 transcribers there. We compare the transcriber, and we see that the inter-transcriber agreement is the same, or almost the same as the automatic transcription. And then we continue further. So the main issue with this algorithm was that the Mark Zonderegger, he wanted to have an experiment, like a closed experiment on linguistics, and he would like to somehow isolate a group of people for a month and see how the VOT changes over the months, because we know there are some phenomena, especially, for example, if I speak with Dan, he has a UK accent, I have Israeli accent, the VOT going to converge like after 10, I think 10 minutes, something like that, 8 minutes, called the accommodation, it's called many things. And he wanted to check that, so he didn't know how to do that until he came up with the idea of the Big Brother. So this is a show in the UK that 30 people voluntarily are located in one house, one room, and they speak together, and it's a very nice place to check their phonetic variation over middle term. So I have to tell you that this is really innovative, because there was no evidence for midterm linguistic study like that. There are other linguistic studies like 10 minutes, and there are linguistic studies of Queen Elizabeth which take years. But something like that which take months, it's something really new. So the speech here is really hard.
Jennifer is in the dining room. What is the atmosphere like in the house?
This morning, everyone seems to be really sort of happy and really.
You got that. She's like have a lot of deletions of the plosives at the end of the sentence. But this is Katria. This is her close enemy, and she has a Filipino accent. This is amazing. Let me explain you why she's hungry. The Big Brother don't let her eat cookies. This is the reason. So this is amazing. This is really a hard speech to work with. So this was annotated at MIT, at University of Chicago, and I forgot where. I forgot where. No, he was guiding students to do that. Maybe. So this is really hard data. This is American accent. UK accent, British accent. So you see the difference between inter-transcriber agreement and the auto agreement, and also the same. And then we continue with that. We take the model and check it on other data set, like the train model on other data set. But what I wanted to show you is how it works with the real phonetic study. So this is one phonetic study which bilingual of Portuguese, which has negative VOT, hence all the VOT is like going down compared to monolingual American speech. So what you see in red is our algorithm, and blue is the manually labeled algorithm. This is huge. This is, I think, I forgot how much it is. This is like 7,000 words, and they hand labeled that. I don't know how they do that. Anyway, it's like 99 correlation, and got the same results, the same qualitative results. The other work that I'm doing now in Northwestern universities with Jeremy Needle and Goldrick. So the thing is the tongue twister. So colliders or particle accelerators are used as a research tool in particle physics. So what you do, you take the elements and you have a very high energy, a very high kinetic energy, and you let them impact with other particle, and then the system goes into extreme state. What we do in phonology, phonetics, is that we use tongue twister. This is like taking the language system into extreme, and we try to look at the errors of those. And this is I think it's this is what they claim, it's the fully automatic phonetic study. The first study, we use the fossil liner, we locate body the location of the plosives, we predict the VOT and have some kind of statistical analysis. Let me show you a demo of that, and by that I will end the talk. So this is something that used to take 1 hour for a person to do. You need to believe me that I took random file from the set. You have no choice but to believe me. Let's put time, how much time it takes. This is fossil lining. They take the transcription automatically. Yeah, that's it. It was very brave that I presented that because it's not like ongoing work. So it took like 3.4 seconds instead of the whole file instead of 4 hours, like 1 hour, sorry. And then if you look at the results, this is Pratt. This is really accurate. You see, this is the VOT for those. So this is clean speech. This is data that is really clean. It's really different from speech recognition because what we need here is really accurate. There is not much noise or something like that, although, by the way, this algorithm is really robust to noise, but the thing is that we need really, really accurate, like high accuracy here. You see, it's like 0.9. It's like the number here is seconds, so it's like 99 millisecond accuracy here. Nothing human here, nothing. We have the wave signal. This was generated automatically because we know the patterns. They say para, 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 or they say bad, bad, bad. This generated automatically. This is the processing window that we give to the algorithm because the forced alignment usually have mistakes and the P can be here or I don't know where. So it's really big. This number refers to this phoneme, which is the 45th phoneme, and this is the VOT. There is nothing like human here. Yeah, we have all the VOTs there, and we could, yeah. So let me finish. The other works I'm working on is on pronunciation modeling when you have the phonemes and you want to predict the word. And we could, like, again, designing features and designing the algorithm, we could go from 60, which is the dictionary lookup, to 14. This is the error. I have another work on speech intelligibility before and after chemotherapy, this tongue twister. I just want to thank my collaborator. This is David McAllister, Tamir Hazan for the direct loss minimization. The VOT is Katie and Morgan, the students, and Chiang and Mark, the students for the phoneme recognition. And this is the phonetic study. This is Jeremy, Natalia, and Matt Goldrick from Northwestern University. Okay, thank you. This is like invited.
Because 90% of the cases that you find in the wild would have negative VOT.
Yeah, this is like an invited question. We have a work that just presented in InterSpeech. I didn't present here for negative VOT.
So just when I look at the curves and I see that, so the sharp part of the curve all falls in the 0 to 15 or so milliseconds.
Yes.
Which of course is the tail of the pre-voice distribution. So how do you account for this? How do you confine your sample to examples that have 0 to have VOTs in that range that you're showing?
So some of the data we took only the initial voiceless stops, and some not. Some it's just the distribution of American English and UK English. But we have a system now. The current system, actually, the results that I show you on the current system, like the demo, was with our system currently handle negative VOT and positive VOT. It's like two systems working in parallel. You can have like also 0 VOT. You can have many things as you wish. And it's working on parallel and give the same results. The problem with the negative VOT that we didn't have anybody to compare with. So we compare it to ourselves. That's it.
Negative VOT is a matter of being able to pick up very, very low signal, very, very low amplitude, low frequency signal, because it's negative VOT has no independent phonemic value, but it occurs all over the place.
Right.
You won't be able to measure it unless you very carefully control the condition.
Yeah, it's really hard to measure that because you don't know the initial locale. We have some results on that, and they look similar to that. We try to give the, so there was guidelines that were given to the phonetician how to mark that VOT, and we follow those guidelines when we designed the negative part of the algorithm, but it probably worked the same as the positive VOT. We use that now. We use that in Spanish data. We use that on, there's going to be a paper on the phonetic study about it, which was again the same results as the human results in that case.
If I understood Jack's question correctly, there were 2 or 3 data sets on which you did the VOT study. One of them was this Goldrick data.
Right.
You had guaranteed that it was a sentence initial stop consonant, right? Because
yeah, I presented only half of that. This data set has a negative VOT, and we presented results on that in the last InterSpeech with Katie.
No, but whatever it is, that data set is prompted speech, right? It's not spontaneous, or is it?
And
the way you described it, I thought that
this is
an initial silence followed by the word, which became.
This is prompt speech, yeah.
Right.
This is prompt, but
So in that case, the examples are what they are. But then, for example, with the Big Brother.
Big Brother and switchword are spontaneous.
How do you choose the examples? Do you actually look for things that are marked with the positive VOT but nothing to the left?
The label was for all examples. We took a sentence and just labeled that. It's not we. It's like was done with phoneticians. And they marked positive and negative. And I think we, in one experiment, took only the positive. In one experiment, took everything. I think what I presented here is with everything. And in one experiment, we took only the negative part, and we checked, like the switchword, I think it was 5% negative, something like that. 4% of the data was Yeah, it was the error. Yeah, it's the relative error in the estimate of the VOT. Like if it's 10 milliseconds, it means like it might be negative. It means like 10 milliseconds of the offset of the transcriber, or several transcriber in average.
Okay, that's why I was asking my question, that rather than show me the absolute error, if you show me an error, because that's how it would become important. That's when it would be important. If half your pixels were
No, it's relative error.
milliseconds VOT, then a 10 millisecond error is a large error. But if very few of them were 10 milliseconds VOT, then and let's say the average was 20, then a 5 millisecond error is a good error.
So yeah, it's like
More worried about how what is essentially a continuous measurement,
Right.
which becomes discrete depending on the language you're dealing with, because some languages have 3 divisions.
yeah, this is the we define it like that. So we define.
That's what I'm worried about.
So if it's negative and this is negative, it still is going to be. Yeah, if this is negative and this is negative, it's still going to be positive. Like we take the absolute value of that. We use the same cost also in the other work. Okay, thank you very much.